Hello friends, in this video let us understand about the switching characteristics of SCR. So let us initially proceed to the definition of SCR. The abbreviation is Silicon Control Rectifier. It is a unidirectional semiconductor device which can be used to provide a selected power to the load by switching it on for the variable amount of time. So it is named as SCR because the device is made of silicon and its operation as a rectifier can be controlled. So according to the IEC, that is the International Electrotechnical Commission, the definition of the thyristor is the device made of 3 or more than 3 PN junctions, and the device which has 2 ideal or stable states, they are on and off. The SCR is a member of the thyristor family, so it is the oldest and well-known member of the thyristor family, and the SCR is so widely used that as if the name thyristor and SCR becomes so synonymous. So although there are many different members in the thyristor family, the SCR is so widely used that people started thinking that SCR is nothing but the thyristor. So coming to the characteristics, the characteristics of the thyristor. The characteristics of a thyristor is a combination of the characteristics of the thyratron tube and transistor. That's why the first 4 letter of the thyristor is taken from the thyratron tube, that is from the thyratron THYR, and the last 5 letters are taken from the transistor, because the thyristor, the characteristics of the thyristor is a combination of the characteristics of the thyratron tube and transistor. So coming to the structure of your thyristor, the thyristor is a 3-terminal device, 3-terminal, 3-junction, 4-layer alternating P-type and N-type material doping. So let us draw this structure here. So it is a 3-terminal device with 3 junctions and 4 layers of alternating P-type and N-type material doping. So let me indicate, this is P, this is N, P, N. So the terminal which is connected to the outer P region is anode, and the terminal which is connected to outer N region is cathode. So here we are indicating cathode with K because we are adopting the German notation as K, and to the inner region, inner P region, my gate terminal is connected. So the symbol of this SCR can be given by, so here is your gate terminal, here is the anode, and here is your cathode. Now coming to the switching characteristics of SCR, so the forward bias thyristor, let me draw the structure once again. This is your P, this is N, this is P, and this is N. So a thyristor can be made in forward bias by connecting the positive terminal of the battery to the anode and the negative terminal of the battery to the cathode. So a forward bias thyristor can be turned on by increasing the positive forward voltage beyond the breakover voltage. So if you draw the VI characteristics of the thyristor, so your VI characteristics, so let me say this is my VBO, this is IA, and this is VA. So similarly you are also having the reverse breakover voltage. So initially if I increase my forward positive voltage beyond the forward breakover voltage, then the thyristor can be turned on, or it can be made enter into the conduction mode. So once you increase the voltage beyond this breakover voltage, the thyristor will come into the forward conduction mode. So the other way of turning on your SCR is just by connecting a voltage source between the gate terminal and the cathode terminal. So this is your gate terminal, this is the cathode terminal. By connecting a voltage source between the gate terminal and the cathode terminal, I can turn on my SCR with a very small voltage. So why a very small voltage is required here, rather than we are moving for a very high breakover voltage in the forward blocking state to make our thyristor enter into the conduction mode. So the reason for why we are employing a, or why we require only a small gate current signal to turn on our SCR rather than the high voltage beyond the breakover voltage. So the reason is, so if you look at the layer structure of your SCR, the SCR can be made equivalent to two complementary transistors PNP and NPN. So if I bisect in this way, then I will get two complementary transistors. So one transistor is PNP and the other transistor is NPN. Now, if you go through the working operation of the two transistor model, you will observe the regenerative action taking place due to the positive continuous feedback effect. So due to the positive continuous feedback effect, when we are applying a small gate current, that is Ig, and this Ig gate current signal causes a regenerative action due to positive continuous feedback in the two transistors, and therefore if I consider my alpha 1 is a gain of PNP transistor and alpha 2 is the gain of NPN transistor, so if you observe the expression for the anode current in the two transistor model, so the anode current will be given by IA is equal to ICBO1 plus ICBO2 plus IG alpha 2 by 1 minus alpha 1 plus alpha 2. Now, if I apply a small gate current here, then Ig automatically increases and my anode current increases, and the other way is, due to the positive continuous feedback, my alpha 1 increases, that is the emitter current of PNP transistor increases, that means my alpha 1 increases, and the emitter current of the NPN transistor increases, that means my alpha 2 increases, and due to the positive continuous feedback, this alpha 1 plus alpha 2 approaches a value equal to 1. So when your alpha 1 plus alpha 2 becomes 0, there will be a large amount of anode current, and this large amount of anode current is caused due to a small gate current signal. Due to the positive continuous feedback, there is a regenerative action taking place. So now moving from the forward blocking state to the forward conduction state, the transition time taken is named as the turn on time of your SCR. So the transition time from the forward blocking state to forward conduction mode is known as the turn on time of your SCR, and the turn on time can be subdivided into three intervals. So one is a delay time, one is a rise time, and the other one is a spread time. Now speaking about the delay time, so in this interval, after the application of the gate current, the thyristors start conducting in a very small region. So over a tiny region, the thyristor will start conducting, and the delay time can be defined as an interval. So let me say about these graphs. So here I am having a VG, that is a gate voltage, so plotted against time. This is time, and time axis. So this is my gate pulse. This is my gate pulse. Initially after the application of gate pulse, the thyristor conducts in a very small region, and the delay time, so here I am having, this is my anode voltage, this is my gate current, and this is my anode current, and this is the power loss occurring in the SCR. So the delay time is defined as the time taken for the gate signal to reach 100% from 90%. So this is your 90% and this is your 100%. So the time taken for the gate current or gate pulse to move from this gate current to move from 90% to 100%. So this time interval is your delay time. On looking it from other point of view, the delay time is also defined as a time interval for which the anode current is moving from the forward leakage current. This is due to forward leakage current. This is the forward leakage current here. So the delay time is defined as the anode current to move from the forward leakage current to 10% of its final value. At the same time, there is a fall in the anode voltage from 100% to 90%. So here you are having 90%, this is 100%. So that means the gate current is increasing from 90 to 100%. Let me write it here. The gate current is increasing from 90 to 100%, and the anode current is increasing from the forward leakage current to 10%, and the anode voltage is moving from 100% to 100% to 90%. So this is your delay time where the thyristor starts conducting over a very tiny region. Now coming to the rise time, so the rise time is defined as the interval in which the anode current moves from the 90% to, that is a 10% to 90%. So here is your 90%. The anode current is moving from 10% to 90%, and whereas the anode voltage falls from 90% to 10%. So the phenomena of falling voltage and increasing current depends on the type of load. So it depends on the type of load. Suppose if, for example, if we have connected an inductive type of load, there is a faster falling rate of the anode voltage compared to the increasing rate of your current. So because initially the inductor, we know V is equal to L into di by dt. The initial value of the inductor doesn't allow the change to the current. So this makes the current to be the voltage falling at a faster rate compared to the current increasing at a slower rate due to the inductor. Now if you are having a capacitive type of load, in the capacitive type of load you will be having a faster increasing rate of the current and a slower falling rate of your anode voltage. So because in capacitor we know I is equal to C into dV by dt, so it doesn't allow the change to the voltage initially. So therefore in the inductive type of load we are having a faster increasing current and a slower falling anode voltage. So now the higher increasing rate of di by dt may create local hotspots. So it may create local hotspot, which is nothing but the concentration of the current in a very small tiny region. So thereby the temperature or the junction temperature may increase beyond the temperature rise limit and it may damage your SCR. So in order to tackle this high increasing rate of di by dt, it is advisable to use a inductor in series with the SCR. It is advisable to use a inductor in series with the SCR. So we have seen the delay time and the rise time. Now coming to the spread time, your spread time is the interval in which the anode current rises from 90% to 100%, and at the same time your anode voltage falls from 10% to the minimum or the smallest possible value. So this is the smallest possible value. This area also represents the on-state voltage drop. This is the on-state voltage drop of your SCR, and here you will be seeing a steady state operation. This is your steady state operation in this interval. Now the spread time is the time, as we seen, the anode current increases from 90% to 100%, and the anode voltage falls from 10% to the smallest possible value, and the gate current remains constant for the rise time and the, or you can say for the rise time, spread time and the steady state operation, the gate pulse is remaining constant in this manner. And during this interval the conduction spreads all over the area of cathode, and the SCR will go to fully on state. So it will go to fully on state, and the spread time depends on the cross section area of your cathode. So if you are having higher cross section area of cathode, then spread times take a little bit more, and lower the area, lower the spread time. So this is about the turn on characteristics of SCR. Now moving to the turn off characteristics of your SCR. So once the thyristor is switched on, or once the anode current, let me say anode current IA is greater than, exceeds beyond the latching current, the gate loses the control over the turn off of your SCR. That means the gate circuit is not capable to turn off your SCR once the thyristor is switched on, or coming from the other point of view, once your anode current exceeds the latching current IL. So in order to turn off your SCR, the anode current should fall below a certain value of current known as IH, that is the holding current. So latching current is the minimum value of current to be attained by the thyristor to maintain its conduction state when the gate pulse is removed, whereas I holding current is the minimum value of anode current, for which if the anode current falls below this minimum value, the thyristor will come to the off state. That means this IH is related to the turn off process and your IL is related to the turn on process. So generally the relation the IL will be equal to some 2 to 3 times of IH. So even when the anode current, let me see here, even when the anode current falls to 0, there is some voltage appearing here. That means the thyristor is not able to gain its property of blocking the forward voltage due to the presence of charge carriers. So due to the presence of charge carriers in the 4 layers, the thyristor is not able to regain its property of blocking the forward voltage. So therefore, for the proper turn off of your SCR, these charge carriers must be swept out, they must be swept out or recombined for the proper turn off of your SCR. Now on the basis of removing these charge carriers, the turn off time can be subdivided into 2 intervals. So your turn off time is indicated by TQ, and it is subdivided into 2 intervals. One is the reverse recovery time and another one is the gate recovery time. So your reverse recovery time is TRR and the gate recovery time TGR. So before going to the reverse recovery time and the gate recovery time, the definition of the turn off time can be defined as the interval between where the anode current becomes 0 and the thyristor is able to regain its property of forward blocking voltage is known as the turn off time. It is nothing but the instant between the anode current falls to 0 and the time when the thyristor is able to regain its property of blocking the forward voltage is defined as your turn off time. So on the basis of charge carriers, we have split or we have divided the turn off time into TRR and TGR. So your reverse recovery time is nothing but the time interval in which the charge carriers from the junction J1 and J3 are removed. So if you see the anode current characteristics, so let me say this is my time T1, this is time T2, this is time T3. So at T1 the anode current falls to 0, and after T1 the anode current is increasing in the reverse direction with the same slope. That is, if I say this is my slope di by dt, so with the same slope of di by dt, the anode current is increasing in the reverse direction. Now this negative current will help to sweep out the charge carriers from the junction J1 and J3, and these at the time T2 the charge carrier density is not sufficient to increase the reverse current further. So therefore, as the charge carriers are not sufficient enough, the negative current starts decreasing. So the value of current at the time T2 is defined as the reverse recovery current, where the reverse increasing current started decreasing due to insufficient charge carrier density. So this interval from T1 to T3 is your TRR. This is the reverse recovery time where the anode current falls to 0 and it increases with the same slope di by dt in the reverse direction, and at T2 the charge carrier, due to insufficient charge carrier density, the negative current starts decreasing and it decreases up to this point where the charge carriers from the junctions J1 and J3 are removed, and due to the rapid decreasing, or you can say the rapid increasing rate of negative current, there you will see a spike in the reverse voltage is seen across the thyristor. Due to this rapid decreasing, or you can say increasing reverse current, you will see a spike across the SCR. So after this reverse recovery time, the thyristor will follow the reverse voltage and regain its forward blocking property. That is a forward blocking voltage property. Now coming to the gate recovery time, the gate recovery time, even after the reverse recovery time in which the charge carriers from the junction J1 and J3 are removed, the thyristor is not able to block the forward voltage even after TRR. So it is because due to the trapped charges in the junction J2, the thyristor is not able to block the forward voltage. So these trapped charges can only be recombined. So they cannot be swept out, they can only be recombined. So the time interval taken for the trapped charges to recombine is defined as or is known as your gate recovery time. So this interval is your gate recovery time. Now you will be having another time, that is the circuit turn off, TC, that is the circuit turn off time. This circuit turn off time TC, which is defined as the time interval between the anode current falls to 0 and the reverse voltage due to the practical circuit reaches 0. So this interval is your circuit turn off time when the anode current falls to 0 at T1 to, let me say this is T4, where the reverse voltage due to the practical circuit reaches 0. So your T4 to T1 is the circuit turn off time. So for the practical circuits for the reliable turn off, the TC should be greater than TQ. So in case you are having the reverse condition where TQ is greater than TC, then the thyristor will turn on at the unwanted instance, leading to a commutation failure in the SCR. So here, speaking of the power loss, the power loss will be the maximum in the rise time, because in the rise time you are having a high amount of current coinciding with a high amount of anode voltage. So this high amount of current and the anode voltage gives rise to a large power loss in the SCR. So summarizing all about the switching characteristics, the turn on time is TD, TR, TS. So TD, the delay time where the gate current moves from 90% to 100%, anode current moves from forward leakage current to 10%, and the anode voltage falls from 100% to 90%. Rise time is from 90% to 10% anode voltage, 10% to 90% anode current, and there will be a large power loss witnessed in the rise time. And in the fall, that is the spread time, the 10% to smallest possible voltage, there is a fall in the anode voltage, and from 90% to 100% the anode current, and there you will see a drop in the power loss, that is a reduction in the power loss in the spread time, where thyristor will go to the fully on state. These are your on state voltage drops. Due to the low voltage, you are having the low power loss. Now moving to the turn off time, you are having reverse recovery time, gate recovery time. Reverse recovery time in which the charge carriers from the junction J1 and J3 are removed. In the gate recovery time, the trapped charges in the junction J2 can only be recombined. In the circuit turn off time, when the anode current falls to 0 and the reverse voltage due to the practical circuit reaches 0, and for the reliable turn off time, the TC should be greater than TQ. So this is all about the switching characteristics of your SCR. I hope you understood well. Please subscribe to the channel. Thank you.